Welcome to the 34th Q-Chem webinar. My name is Dr. Adrian Morrison, and I'm a staff scientist here at Q-Chem. Today, our talk is about the BrianQC 0.8 GPU module for Q-Chem 5, and will be presented by Istvan Ladiansky at Stream Innovation Ltd. It's a brief bit of background before I introduce our speaker. Q-Chem is partnered with the great people at Stream Innovation. They're developing a add-on module for Q-Chem, as well as their own standalone software that can be installed alongside Q-Chem and uses GPUs to accelerate various calculations. To talk about that today is Istvan, and I'll introduce him. Istvan Ladiansky is currently the chief scientist at Stream Innovation Ltd. For the BrianQC project. He received his degree in theoretical physics from the Budapest University of Technology and Economics, BUTE, in 2011. While there, his thesis on reduced scaling Hartree-Fock calculations using tensor decomposition and neural networks was awarded the first prize in the National Scientific Students Association's conference. From 2010 to 2013, he worked at BUTE as an associate researcher and developed the MRCC quantum chemistry program package. And in 2013, he started at Stream Innovation. Before I turn this over, I would like to remind everyone that this talk will be available to view on YouTube if you want to go back and see it again in the coming days. Also, I'd like to encourage anyone to post questions. Anytime throughout the talk, there's a little question box in the GoToWebinar control panel. At the end of the talk, I will relay these questions to the speaker. Without any further ado, I think I'm going to turn this over to Istvan and let him give his talk.
Okay, so thank you so much, Adrian, for the kind introduction. And I would also like to greet the audience. If you're here with us from the US, then good morning. If you're here with us from Europe, then good evening. And if you're here with us from Australia, then you might be a night owl and really into GPUs or quantum chemistry. So thank you for joining us. As Adrian introduced me, I'm Istvan Ladiansky, and I'm the lead scientist at the BrianQC project. And I would like to thank the organizers for this opportunity for us to show our work to the Q-Chem community. And as you must hear from my voice, I'm quite excited. So without further delay, let's just start. So, brief introduction of our project. Around 2010, people in the quantum chemistry community started to be interested in implementing quantum chemical calculations on GPUs. And a few research groups who had the expert knowledge back then started to do their own implementation of quantum chemical algorithms on GPUs. And in 2013, the BrianQC project started as a spin-off project of Pázmány Péter Catholic University, and Furukawa Electric Institute of Technology catalyzed the project, no pun intended, from the beginning with expert knowledge and funding. And in 2015, we started a collaboration with Q-Chem, and in 2017, we started a collaboration with NVIDIA. So first, I would like to give a brief introduction. What is the BrianQC module? First and foremost, the BrianQC module is a GPU module for Q-Chem. By that, I mean BrianQC can be used as sort of a backend for Q-Chem, where it can do the heavy lifting for different parts of the algorithms, and it can help different code passes to run faster if you have a GPU in your compute node. First and foremost, we started to implement the two-electron integrator part of the BrianQC module. This can evaluate electron repulsion integrals over Gaussian type orbitals. Currently, the Coulomb and the exchange parts, the exact exchange part is available. Also, this integrator is capable of evaluating high angular momentum orbitals So in the upcoming release, which is going to be 0.8, which going to be released with QChem 5.1.2 in a few days, this integrator can evaluate functions S, P, D, F, and G type functions. So quadruple zeta-sized functions are available for calculation with this module. Also, because we can accelerate the 2-electron integral evaluation, we accelerate the DFT code pass in QChem. However, currently we do not have an exchange correlation part on GPU. As I will show you later on the measurement data part, the DFT module is accelerated by the BrianQC module. We also have first analytical derivatives of the Hartree-Fock and DFT level energy. These analytical derivatives can be calculated over S, P, D, and F type of functions. So as usual, the angular momentum is lower by 1, but the derivative is higher by 1. So first analytical derivatives up to F function, geometry optimization up to triple zeta sized basis functions. The BrianQC module can also be used from QChem to speed up those calculations which uses higher order numerical derivatives by evaluating the first analytical derivatives several times. QChem is able to generate the higher order numerical derivatives. So BrianQC can speed up your vibrational calculation, or in case of third derivatives, anharmonic or Raman spectra calculation can be carried out GPU accelerated in a GPU accelerated manner. Also, BrianQC contains a diagonalization module, which is a general diagonalization module, which can be utilized, of course, not just in the Hartree-Fock and in the DFT parts of QChem, but in any quantum chemistry algorithms where diagonalization is carried out. So, as I said earlier, these are the features of the BrianQC module, but from the user's perspective, much more algorithms are speeded up because these basic building blocks can be utilized from various code passes. So, what is the relationship of BrianQC to QChem? What is the vision here? First and foremost, as I said earlier, BrianQC is a GPU module for QChem. So you can think of it as a backend for QChem, and we target those parts of the quantum chemical calculations which can be first utilized by a large varieties of code passes to accelerate as much algorithms as we can. And second, we try to target those parts of the algorithm which are the most time-consuming steps of those given algorithms to gain the most speed up. So this is BrianQC as a backend of QChem. Because QChem is a feature-rich proprietary software, there are various use cases for it, and QChem is used in the last 25 years in a wide variety of computational research, from material science to quantum chemistry through pharmaceutical research. So it's a very feature-rich program. And BrianQC is a GPU quantum chemistry library which can speed up some of these algorithms by providing these basic building blocks I showed you earlier to be calculated on GPU. So by having QChem plus BrianQC, if I want to seem like a marketing person, I can say that this is best of both worlds, because QChem's features and BrianQC's speed can give you a research tool where you have a very feature-rich software and some parts which are basic building blocks will run on GPUs. So this is the basic vision here. After establishing what is BrianQC from a a usage point of view, I would like to show you some measurement data. These are well-known real-world molecules, 5 of them, which we measured for this first slide. This is cis-decolin, taxol, fullerene, valinomycin, and olestra. These molecules are in different size ranges, as you can see from the quite different runtimes from 10 minutes to 8 hours in the case of olestra. These calculations are all carried out in CCPV-TZ, so it's a triple zeta basis set. So these calculations involved F functions. The measurement hardware were in the CPU case 8 cores of an Intel Xeon E5 2620V4 CPU, which I think we can say is an upper mid-range CPU, and it was an upper class CPU approximately 2 years ago. It was leader of the pack, I guess. And the GPU here on all measurements is an NVIDIA GTX 1080 Ti, which is also today a high mid-range GPU, and it was approximately the leader of the pack 2 years ago. So I think this is a fair comparison. It's like apples to apple. So for all molecules, you can see that there are 2 bars. The lower bar is for the CPU calculation on this 8-core CPU, and for the upper bar is the GPU calculation, which were carried out on 1 GPU. And this is all in triple zeta basis set. So after we see that BrianQC can speed up your calculation in these cases, I would like to give you a few insights on how we did this. So for implement BrianQC, we had to first write a full compiler. And to understand why we had to write a compiler, first I want to tell you a little bit about what is a compiler actually. So the first, which we have to establish, that a compiler is not a code generator, and the compilation process is not just the code generation process. In case of a code generation process, you have a source code template, like a text file, where you substitute various variables or values or put in some other parts. But this is basically just a text template substitution. This is what we call code generation. And the code generation is basically a subset of the compilation process, because instead of doing this code generation only, the compiler's main difference is that it has an internal representation. The internal representation is basically a representation of the mathematical expressions which you want to evaluate. You can think of it as an expression tree, for example, is a well-known example can be. And this internal representation is inside of the compiler system, because it can be transformed for the need of the user or the need of the calculation or the limitations of the hardware and software tools. So this is a step which you clearly cannot do if you only have a source code generator, because you have to transform your code to optimize for further needs. And this optimization is carried out by something which we call, which can be called a computer algebra system. So if you want to think of a well-known computer algebra system, you can think of Maple, for example. You give in your expressions and it twists and turns and substitutes and simplifies and does whatever to optimize those expressions, and then at the end evaluate them. But all those expressions are semantically the same. They evaluate to the same value at the beginning, at the end, but you can optimize and transform and twist and turn those expressions according to your need. And so this computer algebra system does all these transformation steps, which I'm going to tell in a minute. Why do we need them, and what are these transformation steps actually? And at the beginning, at the end, sorry, we have this box, which you see the machine learning writing on at the right part of the generation time part of this diagram, which benchmarks all these different kernels we generate, and we store this information for later use. So from the left to right, I want to show you how an integral evaluates. I will tell you this by assuming we only have one integral, this ABCD electron repulsion integral. But in case if you have a bunch of integrals, for example, a tile of the electron repulsion tensor, then the theory would be the same behind this, but it's easier to understand, I guess, if we think of only one integral. So this integral enters the first box, which is the brush root generator in IR. This is basically the part where we first translate the integral expression into internal representation. Then we generate a large variety of so-called roots from this expression. These roots are basically the same expression if you think of it semantically, so they will evaluate to the same value, which currently is the integral's value in the ERI tensor. But these roots differ from one another in several attributes. For example, to give you an example, the same integral can be evaluated by different types of recursion algorithms, which are well known, like the Oberashaika, the Head-Gordon-Popel, or the McMurtry-Davidson, or other integral recursion rules. And if you have a GPU, for example, so this is the algorithms is one dimension of these roots. And in case of a GPU, you can always calculate in double precision or single precision based on your precision needs, or for higher angular momentum orbitals, you also have the Riesz algorithm. And there are many, many other attributes. And based on these attributes, for the same integral evaluation, we generate large number of roots. To give you an example, a few hundred of these roots are generated for the same type of integral. Then all these roots are going into this computer algebra system, which transforms, optimizes, and then generates some code. Transformation means that we are looking for common sub-expressions to put them into temporary variables, or unrolling some loop, which means that the loop are not into a loop anymore, but we are rolling it out into sequential code blocks, or code syncing or code lifting. These are well-known transformation rules in this computer algebra system. The point here is that the expression is still the same. It evaluates to the same integral value, but it differs in memory access patterns, in complexity, and in many other attributes like these. And after this transformation and optimization, we do the code generation for all the roots. As you can see, this computer algebra system is capable of generating C, OpenCL, CUDA-C, and PTX codes. The CUDA-C and PTX is with bold font on this slide because these are only released in the current 0.8 release. But as we are stepping towards BrianQC 1.0, we are planning to release the C codes to support not just GPUs, but CPUs with our own integrator, and the OpenCL part. So we will be capable of running on AMD GPUs, not just NVIDIA GPUs. So we generated the CUDA and the PTX kernels. These are all go into the machine learning box, which benchmarks all these kernels in various situations and on all the GPUs which we are optimized for. And we create a so-called kernel database from this. This is generation time. And in runtime, you have your kernel database installed on your machine. And in the machine learning model, which you can see, enters an integral value, and we know the type. the type here means that we know the angular momenta and the contraction degree on all the four centers of the integral. This identifies a type. And we also know what is the GPU, so we know the underlying hardware which we are going to run on. And the machine learning model can choose for a different integral type, and for a given GPU can be choose the best binary root, which in this case the root I, and it can run on the GPU called J. And when you evaluate this kernel on the given GPU, you get the Fock matrix result, the Fock matrix contribution, which is the result. So this is quite complex, and at this point, I'm not sure if I prove that it's really necessary, because we had to take this detour, but it took years. So I want to give you a few points why we did it. So do we really have to do this? Yes, of course. That's why I'm telling. And so a few examples. First, GPUs are a very special hardware, and the vectorization process is non-trivial. So what do I mean by this? Vectorization is a process when an algorithm from sequential evaluation, you somehow turn it to parallel evaluation. For example, if you look into a 2-electron integral evaluation code, you will see loops. If you look into a tensor equation, a tensor expression, you will see loops. So when one of these loops are not evaluated sequentially, but you put it in a parallel manner on a vector processor, this is the process of vectorization. And by non-trivial vectorization, I mean that it is easy to think that, okay, we have a loop over the integrals, so instead of evaluating one integral, as I did it on one core, now evaluate 100 integrals on your 100 vector cores on the GPU. Now this won't work, because when you evaluate similar integrals, you will have very similar so-called common sub-expressions. And evaluating these common sub-expressions 100 times parallel is a waste of computer resource. So the natural index for vectorization, which goes over the integrals, is a very bad choice, actually. So we have to generate roots, which I showed you on the slide earlier, where this vectorization index differs from one another. This is one thing which the computer algebra system does. And another point of view is that the compilation process on GPUs is not as robust as on CPUs, which means if you write a C code and try to compile it with GCC, with Clang, or Intel C compiler, it is really hard to write C code which will halt your compiler, and the compiler just cannot compile it. It's really hard to write C code like this. But it is not that hard to write GPU code which won't compile, because the NVCC compiler first is not as old as these CPU compilers, and I will show some other attributes of the quantum chemistry code why this is not as robust in the case of GPUs. So when we generate 100 of these computation roots, a few of them will thrown out because the compiler cannot even compile them, although they mathematically are optimal in some way. And the other thing is that quantum chemistry code is weird compared to normal GPU code. And I know it's weird that I'm saying it's weird, but it really is. It's weird in a sense that practically a computation is builds up from two parts. The one is where you have sequential code blocks. When the computer don't have to think of, okay, what is the next expression I have to evaluate, it just first adds two numbers, then multiplies another, then adds another two numbers, whatever, and goes sequentially, no jumps occur. The other is when branches occur in the code, like in a case of an if or a loop, where a computer have to think, okay, what is the next expression I have to evaluate? Do I have to jump? Do I have to go on the true, on the false side, whatever? So in a normal code, you have a few hundred sequential code lines and then a branch. And these are what compilers optimized for. In quantum chemistry code, you have 100,000 lines or even approaching 1,000,000 lines of this sequential code and then one branch. And for the ratio of this branching and sequential code blocks, GPU compilers and all other compilers are necessarily sensitive. So the compilation process is not just the weak point. Quantum chemistry code is weird for the GPU compilers. So I think this is the theoretical background, how BrianQC generates these different code paths and then throw out a few of them and compile other ones and choose between them in runtime. So I would like to show you some measurement data. These molecules, which I show you on the screen, are so-called random branching hydrocarbons or random branching alkanes. We choose these molecules as our test molecules because they can be first generated randomly for very different system sizes. And the different size of these alkanes are chemically very similar, so the chemical variability is basically switched off, and we can generate any shape or any size we want. These which I currently show you are generated to not be long chains, but more like spherical structures. So this is not some trickery with the screening algorithm. These molecules screens as some other real-world molecules. So first, I would like to show you the timings and speedups of the Hartree-Fock self-consistent field algorithm when run with the BrianQC module. These are all these random branching hydrocarbons, which I told you earlier, and the system size goes from 5 carbon atoms and the corresponding hydrogens, of course, up to 400 carbon atoms and the corresponding hydrogens, of course. So the number of basis functions goes from practically 0 to a little below 10,000. All computations were carried out in CCP with DZ, so double zeta sized basis sets. The red line, as you can see from the legend, is the 8-core Xeon CPU run, which utilizes only the CPU Q-Chem. This processor, which I told you about earlier, is a high mid-range CPU, and we utilized 8 cores. So I think we can say this is some fair comparison. In case of the Hartree-Fock algorithm, the NVIDIA Tesla P100 is the fastest card, which is, I guess, not a surprise for you guys as well. So, I also would like to note that if you take a look at the total SCF volt times, these calculations, the large ones, took hours. So these are not toy systems. These are systems which I think can be interesting for a quantum chemist. The same data on the next slide, where I want to show the speedups. So the red line is at the constant 1 height. This is still the CPU run, and all other GPUs or all other runs compared to this constant 1 magnitude. So the speedup can be seen on this slide. I would like to note that these are the same, of course, the same system, the same basis, the same everything. So as you can see, the P100 is around 10,000 basis functions, is more than 7 times faster than this 8-core Xeon CPU setup, which means that around 10,000 basis functions, Tesla P100 can give you the performance of almost 60 CPU cores if we assume that the parallelization between cores is linear. And of course, not just Hartree-Fock, but DFT is one which can be accelerated by the BrianQC module. In this case, we used the same molecules, the same basis set, but the method is density functional theory, and the functional is B3LYP. Still, I want to point out that the computation times are ranging from practically 0 to over 12 hours, so these are not just toy systems. And in case of the density functional theory calculation, the speedups can be seen on this plot. The CPU is still at the constant 1 height with the red line, and in case the NVIDIA GTX 1080 Ti is the fastest card, and it almost goes up to 6 times speed up. So although we are not accelerating currently all parts of the DFT Fock matrix building, the speed up is still 6 times. So an NVIDIA 1080 Ti GPU can give you almost 50 cores of this sound CPU's performance. I also would like to point out that these speedup curves are not saturating in case of the fastest GPUs. These are not saturating around 10,000 basis functions. And as our measurements shows, these lines are going to separate around 50,000 basis functions at a magnitude of speedup approximately. Okay, so we've seen that compared to QChem, we have these speedups. But I think the question, okay, but what about TaraCam, naturally comes up in this discussion. So we wanted to measure ourselves to TaraCam. All the information which we used from TaraCam are publicly available from the website. We downloaded the logs which we gave on the URL, which I put in on this slide. And in this case, the computation basis set is 631G star. I would like to show you calculation in basis sets which contains higher angular momentum orbitals, but currently I cannot find any data on TaraCam how it performs on higher angular momentum basis sets. The computation hardware in both cases were the GTX 1080 Ti, 1 GPU to 1 GPU. So I can say, I think we can say that on this plot, we see an apple-to-apple comparison. As you can see from the speed up numbers, the red line is TaraCam, the blue line is BrianQC. So I think we can say we have a break-even against TaraCam. So QChem plus BrianQC has a break-even against TaraCam's publicly available information. Up until now, I only said you measurement data, so I want to show you a little bit about the financial aspect of this project. In this slide, I would like to show you two scenarios. So at the beginning, on the left side, we have an Intel Xeon E5 2620 V4 CPU. This is the one which I showed you all the measurements on. 8 cores, and of course for this you have 8 cores of CPU QChem license with academic prices. This whole setup, just the CPU and the QChem license, no other parts of the computer, costs you approximately $2,000. Now we have two scenarios here. The upper one is where you basically double your configuration. So you buy another of these Intel Xeon CPUs, so you have 16 cores, and you have a QChem academic license for these 16 cores. You have to spend $880 more above this basically $2,000 to double your configuration. And in the other scenario, you still have your Intel 8-core CPU and you still have your QChem license for 8 cores, but instead of doubling it, you buy an NVIDIA GTX 1080 Ti and a 1 GPU academic license for BrianQC. as it can be seen from the slide, you have to spend approximately $300 more to get the BrianQC set up instead of doubling your own. All the prices here are from Amazon.com, so you can check the numbers. But what do we actually get for this money? So here you can see 4 real-world molecules, which I showed you earlier: toxol, fullerene, valinomycin, and olestra. For all molecules, we have 3 bars. The downmost bar is the 8-core CPU Q-Chem run, still the same 8 cores of this Intel Xeon E5 CPU. The middle bar is where we have 16 cores of this Intel Xeon CPU, and the upper bar is, which is kind of purple, is the GTX 1080 Ti. So we have 1 GPU in the system. 2 things which I think have to be noted here. The first is that Q-Chem almost parallelize linearly in these setups, because by doubling your setup, you almost get double the performance, which is very good. So, and the other thing is that by having just 1 GPU and utilizing it in Q-Chem, you will get these 4 to approximately from 4 to 6 times speedups, which I showed you earlier on the slides. So based on the user's preference, for a little bit more of money, you get more performance, so everyone can decide. And after all this data, I hope you all want to install the BrianQC module as soon as possible. So I would like to show you how to install it, but let me show it in a video. By the way, this video is going to be posted on our website in a few days. So if you want to re-watch it, then you will have the opportunity. So in order to get the BrianQC module, first you have to visit our website, brianqc.com. And in the lower right part, you have to give your email address and your name in this floater, basically. These are for the license. Okay, and your address. I'm not sure whose address it is. Okay. Then a phone number. Click next. And then here we can see that the drop-down is glitches a little bit, but it works well. Just something with the provider, I'm not sure. So choose that. And one thing which we have to note here is the only platform which can be used currently, which we support currently, is Linux. So please leave that unchanged and click submit. Okay. After that, we got a little message. First of all, thank you so much for installing the BrianQC module. And the other thing is that we sent an email to you with additional steps for the installation. So let's see the email. Oh, it's arrived. Great. Yeah, so what's in the email? So in the email, we find 2 scenarios. One is when you're a current Q-Chem user and you have a Q-Chem license and an order number in the time of the installation. The other is when you're a new Q-Chem user and you don't have a license and an order number. I will show in this video the current Q-Chem users scenario, but the other scenario for the new Q-Chem users will be posted on our website a few days from now on. So I'm a current Q-Chem user, so I have an order number and the Q-Chem license. So I just click, I guess, for the script. Great. Okay, you can keep it. It won't harm your computer, I promise. And go to the command line to start the script. Great. First, give them executable permissions and then start it. So this is the well-known Q-Chem installer. I don't want to give you much more information on this. If you're a current Q-Chem user, you know this installer very well. But have to stop here for a second. So when you choose the different Q-Chem types, you have to look in the description for the NVIDIA GPU support. And please note that from release to release, the numbering of this list can be changed. So don't press just 5. Automatically look for the NVIDIA GPU support in the description. So in this case, we will choose 5. Yep. And it started to download. It's speeded up a little bit for convenience. Okay. The installer still, yep, it's great. Yeah, we agree. Okay, so here we are going to enter the order number and the email address. So please note that this order number and email address will only for educational purposes. After this webinar is published, it will never ever result in a QChem license or in a BrianQC license for you. So this order number and email is only for educational purposes, but please use your own. Yeah, this is correct information. Okay, and we're in the BrianQC installer now. You can see that the BrianQC 0.8 module for QChem is installing. These are some general information, website, email addresses. Okay, software environment is okay. And the first interesting part is this list of GPUs. So for your computation node, you have to choose from this list which kernel database you want to install. And here it says, for example, number 2 is the GeForce GTX 1080 Ti and similar. It means that it was benchmarked and optimized for the GTX 1080 Ti, but it can run on similar GPUs. And by similar, I mean when the same architecture number is given to a GPU, which you can look up on Wikipedia, then the kernel DB will run on it. But if you're not sure, please send us an email and we will help to choose which kernel database for which GPU. Okay, so this list is the first which we have to be aware of. The second interesting part here is this line, which is going to be highlighted now, which is printed by the system. So it basically says, we found, because this is the hardware detection part, we found in your system a GTX 1080 Ti. We have an optimized kernel DB for it. If you have another GPU here with the same architecture number, it will says we have a compatible kernel DB for it. And the system thinks the install candidate for this is 2, which I think is correct because 2 is optimized for the GeForce GTX 1080 Ti. Please note that if you're installing the BrianQC module on a cluster head node, then it is normal that no calculation device is found in the cluster head node. In this case, we of course cannot detect your computation device because it's not in the head node. You have to choose it for yourself based on what GPU you have in your compute nodes. So, okay, so here is where you have to choose. We're going to accept the 2, which is the default. And we're downloading all the kernels. Yep. And the installation is successfully finished. A good proxy, if we print out that it's successfully installed, then I hope it's successfully installed. And the other thing which I have to note here is that everyone who installs the BrianQC module has an assigned contact person at the company. So if you have a problem, a bug report, or just want to say that this is an awesome piece of software or whatever, you have this assigned contact person and they can shepherd all your problems through our system. Your email won't bounce from department to department. So please email this assigned contact person and they will help you through the system. In this case, as I see, I am my own assigned contact person, so I think it's a nice choice from the system. I will help myself. Other than that, the installation is finished, and I think the natural question here is how can we test it? So first, you have to have a license. Because this is the scenario for the current QChem users, we have the QChem license in the time of the installation. So we just go into the directory where it is and copy it to the place where QChem normally looks for its license. And after that, we source the qcenv.sh, which is, of course, normal, because QChem runs normally need to source this environmental variable script. So in this case, we source it like this, and then we can try out QChem by invoking QChem-GPU, which means that the GPU module will carry out the calculation. And during the installation, we put a test file into your directory, so you can use this test new install.in file. So let's invoke this command. Great. Okay. So here I would like to add that this part of the video is not edited, it's not speeded up, it's nothing. It's the same experience when you will have if you run the BrianQC module on the same hardware. The good proxy that BrianQC is working under the hood, if you see these lines, which are definitely came from our logger and distinct from QChem's normal messages. So in case you can see that we initialized ourselves for the GTX 1080 Ti. This 3 threads not means that we are using 3 computation devices. This means some other technical issue. So, okay, I think we're iterating through convergence. Great. And yep. So in case of a new installation, the first thing which you have to check is the total energy. Of course, it has to be the same in the case of a CPU and the GPU calculation. And the other thing which you have to check is the total job time, because in case of a GPU calculation, the total job time have to be smaller than in case of a CPU run. But please note that this system, this is only for testing purposes. It is a small system, so small speed up will you experience. If you want to test the speed up capabilities of BrianQC, then please use a bigger system for benchmarks. And I guess this is it. So we have installed and tested the BrianQC module in approximately 3 minutes. And because the module is currently 0.8, I would like to show a few steps which we are going to take until we reach BrianQC 1.0. First, we are working on the one electron integrals over Gaussian type functions. We are going to have an improved DFT because we already accelerate DFT calculations in QChem, but we are working on to put the exchange correlation parts on GPU, which will further speed up the DFT calculations. We are going to release a Windows support because we know a lot of QChem users are using Windows boxes, so we don't want you to work without GPU support. We are also going to add higher angular momentum integrals over Gaussian basis functions, H and I functions. So those who want to work with, I don't know, 6 zeta basis functions, basis sets, can integrate them on GPU. We are going to further accelerate the first analytical derivative, so the numerical derivatives and geometry optimization module will be much more faster in 1.0. We are working on an analytical second derivative of the energy in case of Hartree-Fock and DFT. So vibrational analysis no longer need the numerical second derivatives. And also we plan on release a molecular mechanics module for biochemistry applications, for example, or pharmaceutical applications. And also, if you have a QM, so a quantum mechanics and the molecular mechanics module, it is a straightforward step to take to have a QM-MM module. In our case, it's Onion. So before we wrap this presentation up, I would like to introduce you the team, because I did the presentation, but of course, BrianQC is a work of many, many people. I will only show you the core team. So first, József Illés, our CEO, who actually makes the cash flow. Then György Cserei, our CTO, who basically serves as a father for all of us in the project. Then Ádám Rák, our lead developer, who is the only person I know who has CUDA as native language in his ID. I, myself, István Ladnyánszky, then Gergely Kis, our software architect, who will mostly reject your C++ code based on style reasons, Gábor Tornai, the most charming smile in the project and the best staff scientist on our team. You are lucky to have him an assigned contact person at the end of the installation. And Benjamin Cétényi, who is a developer, but not just a developer, who is the one who keeps alive the Python ecosphere, which generates benchmarks, tests, deploys, and whatever this monstrosity, which I have been talking to you in the last almost 1 hour. So if you're still with us and have any further questions, I'm keen to answer. Thank you so much.
Thank you, István, for that informative talk. Very impressive work. I just want to remind everyone that if you came in late, you can watch this webinar again later on YouTube in the coming days. We have time for a few questions. We have a few already, but feel free to punch them in the question box here. All right, István. A few people are curious to know internally what level of floating point precision is used by the BrianQC module.
Sorry, can you, what level of? Sorry, the audio.
What level of floating point precision?
Okay, so these calculations, which I showed you, are mixed precision calculations, which means in the roots, which I showed you in the compiler slide, which I'm going to show in a second. So here in the roots, we have full single precision kernels, full double precision kernels from all the algorithms, and we have mixed precision kernels, and we have heuristics which chooses between the roots in the machine learning model, which not just benchmarks for performance measures, but only precision levels. So we do not, we cannot lose any precision compared to a CPU implementation, but we utilize as much floating point kernels instead of double precisions, or as much mixed precision kernels as we can without losing precision. So this information is provided by the machine learning model in the runtime. I think it's, but if it's unclear, I can elaborate on this more if there are any other questions regarding this.
I think that works for me.
Okay.
Thank you. What would you say a recommended minimum system requirements, minimum hardware level to see improvements with BrianQC?
Okay, so I think the CPU part, I don't have to tell much about it. We showed that we have this upper mid-range 8-core CPU, and we have this in a cluster in approximately 20 nodes, and we are quite happy with it. So I think you don't have a monster CPU. You have to have it, of course, because Q-Chem utilizes CPU heavily. And if you do some calculation, which we are not accelerating entirely, which is basically all the algorithms in Q-Chem, then you have to have a good CPU. And in GPU, I can say that I'm not sure if NVIDIA is happy with this statement, but gaming cards are best suited for quantum chemistry, because for this precision to reach, which I told you earlier, we found that only between 5 and to 10% of the integrals have to evaluate it in double precision. And if you check the cores in today's gaming cards, then the ratio of double precision to single precision processors is almost like this. So I first think that gaming cards are best suited for BrianQC, and in the Pascal series we measured that the 1080 Ti were the sweet spot, and as soon as we can put our hands on a Volta or Tesla series, then I think we were also go for the high-end gaming cards. So 2080 Ti, for example, I think these are the best cards for BrianQC. But just to give a little story about it, in our development computers, we have 1080 Ti's for computation, and we have a 1050 for display. And once I forgotten to exclude the 1050 in the config file of BrianQC. So as it's greedy, it started to utilize it. And on a 1050, we gained Speedup as well. So if you're on a budget, you can start up with anything. And maybe later on, I'm not sure if I can say anything about this, but later on, I think cloud support will help users to test our product on budget, I guess. But it's something which later will happen, I guess.
Thank you. Yes, that's convenient about the gaming cards being very appropriate.
But as I showed you on the measurement data, of course, a Pascal P100 is faster, but it's again a trade-off based on user need between budget and performance.
Of course. Sort of along those lines, what would you say, we can refer to the graphs in your slides for this, what would you say is the smallest number of basis functions in a system that exhibits a speedup with BrianQC?
I think according to our test system, I think it's around, okay, so I think against 8 cores of CPU, we have a break-even around 300 basis functions. I'm going to those slides and we try to take a closer look to the grid. So yeah, as far as I can remember, around 200 to 300 basis functions. So this is 2000, then this is with a 400, 800. Yep, that's so. Yeah, so around 400 for slower cards like the M60 and the K80. I mean, not slower, but older cards, around 400 basis functions. We have a break-even, and for newer Pascal cards, we have it around 200 to 300 basis functions. But of course, as you can see, the beginning of the speedup curve is quite steep. So I think if you want to see a speedup of 4 and you have this 1080 Ti, you have to have a system somewhere below 2000 basis functions, 1600, I guess. So it's a fair speed up at 4. The break even is around 200 to 300.
Great. Yeah. So you really start seeing speed ups right away with a couple hundred basis functions.
Hopefully, yeah. I hope. But definitely not in the test install, because it was designed to run in a few seconds to show that everything is up and running. So if you invoke the command at the end of the installer and you find that it's only faster by a few %, then this is not the aiming here. It's only for test purposes. So calculate your own system which you're interested in.
Sure. We're a little over time, but there's a few more questions. If you don't mind, I'll keep going.
Yeah, sure.
Let's see. So we have a few questions, and I can comment on this from the QChem perspective if you want. But is BrianQC compatible with MPI?
Okay. If you want to add any comments, I'm happy to have you here.
Sure. So I am.
And after that, I will comment on that as well.
Okay.
If you think.
So I'm fairly certain you can back me up on this, that BrianQC module does support MPI. However, in this current release, it hasn't been fully integrated. The MPI functionality isn't fully integrated into QChem, but that's something we are looking to rectify in the near future.
Yep, yeah, absolutely right. But I I didn't want to say the QChem part. But as far as I'm concerned, the QChem part is currently not ready for MPI evaluation. This is something which we're working on. But I wanted to tell that in one node setup, all these speedups which I showed are with one GPU, but with a cheap motherboard even, you can put easily 4 of these GPUs, 4 of these gaming cards, because these are not 3-unit cards. These are most of the time 2-unit cards. You can put 4 of these into a box, and because BrianQC speeds almost linearly for these 4 GPUs, if you utilize 4 GPUs instead of 1, if you have a large enough system to give enough work for the GPUs, without the MPI implementation, you can have 4, or in a server machine, even 8 cards which can work together, and the very first speedup can be reached on one node. And as you said earlier, we are going towards the MPI parallelization. So parallelization between nodes will be, I think, available in 1.0 as well. If you'd like, yeah.
Okay. Yeah. Just maybe a couple more quick questions. Let's see. How does BrianQC module perform, or do you have any experience with heavily contracted basis sets such as ANO?
I don't have data on this specific basis set, but because the screening model of ours is basically not the same, but it's semantic. So most of the screening algorithms, which are well known in the CPU world, we still have on the GPU implemented. Of course, we had to twist and turn these to vectorize for our needs, but the same screenings, for example, density screening and Cauchy screening and Shelper screening are built into the BrianQC system. So the same screening algorithms work here, and we added just one extra screening algorithm here. So I think if you have curves, how the CPU handles these highly contracted basis sets, I don't really see any cause why the GPU would suffer from this. But I don't have the data on me, but this product can be freely tested. So we are inviting the user who asked this to download and test with these basis sets, and I'm happy to receive any information on this. So yeah.
Okay, thank you. I think we're running out of time here, so I will bring this to a close. If you have more questions, you feel free to email me or get in touch with the BrianQC developers.
Yeah, sure.
Thank you again, Ishvan, for that really informative talk and the great work you guys are doing.
Thank you for the opportunity to show our work.
Of course.
Okay.
Thank you to all the attendees for watching today and asking questions. This is actually our last webinar for 2018. So if you've been with us for a few of these, thank you again, and we'll see you again next year. If you came late or you want to view this again, it will be posted to YouTube in the next couple of days. You can find our webinars on the Q-Chem website under this tab. They are all listed here. This current one will be posted soon. Also, feel free to check out our instructional materials. These are useful for learning the basics or for teaching purposes. Also, note that on our homepage, you can find a link to the BrianQC website now. Thank you again, everyone.
This concludes our webinar. We would like to thank Istvan Ladiansky for his excellent presentation, as well as Dr. Adrian Morrison for organizing, running, and moderating this webinar. We also invite you to visit us on Facebook. Thank you for your participation, and see you at the next webinar.